Hello and welcome back to Calculus 1, section 4.4 on graphing functions. So the goal here is to learn how to graph functions without using software. And it's not functions x squared or x cubed or sine x, which are the functions that you have memorized. These are the functions that are obviously more involved. Let's say ln x squared. Let's say, well, ln x squared is easy. Actually, you just put 2 in front of ln x and just graph ln x. But, you know, let's say sine of e to the x and stuff like that. So how do we graph these functions? Well, all of the functions which we studied, and also those that we did not study, follow the same rules. Those rules are increase, decrease, concavity, x and y intercepts, asymptotes, right? So all of the functions have to bend around and go through the points and then bend around the asymptotes and so on. So we have a very systematic way to graph this. Now you will see that these problems tend to be long and annoying, because there are a lot of calculations, and clearly you can use technology to do this job much faster. However, right, with the use of technology and consistent use of technology, you lose that analytical portion where you have to critically think about the graph and increase and decrease and all that quality things that the graph shows. So that means that learning how to graph by hand is useful because you will know more about the graphs in general and what do certain features mean, and then be able to connect formulas to graphs and those qualities of the graphs much better. Now, I call this the shopping list. And it's mainly the list of things that we need to compute so that we can really do the easily, right? So that we can really do this graph, so we can do graphing. So number one, I would say domain. Also range maybe, but not so much. Domain is very important because you need to know what are your values that you may use as an input right into this calculation. Number two would be x and y intercepts. And x and y intercepts would be what we studied all the way back in algebra. And then we're going to have asymptotes. And we have 3 of those. We have a vertical. Let's start with vertical. Horizontal. And slant. Now, slant or oblique asymptotes are very rare because they only show up for one particular group of functions. And there is also another restriction that those functions, right, which are polynomials, the degree in the numerator has to be by 1 bigger than the degree in the denominator. We will see the example, but those asymptotes are very, very rare. Now, obviously, we're going to pick an example that has it, so we can see that as well. So we started with the domain, we went into x and y intercepts, and then we went into asymptotes. And now, number 4, well, I'll say get f prime and f double prime of x or whatever. So find the first and the second derivative, so that number 5 you can do your first derivative test, and then for number 6 you can do your second derivative test. For number 8 you might want to consider symmetry, which is technically even and odd talk from pre-Calculus 1. And then number 9, maybe you need additional points. And then finally 10, graph, and win. Right. So that's the list. Now,
And
if
there's
you
no 7?
what happened?
There's no 7?
There is 7. There we go, 7. Now you're gonna say there's no 8, then I have to fix that one.
There's no 9.
See, there we go. Come on, I'm waiting. I just need one troll to say, well, there's no 10.
Is there any 10?
There we go, thank you. Now that makes my day. Is there any 10? Okay, good. Thank you. Now, this is actually 13 different calculations if you consider all of the asymptotes separate and then the first and the second derivative separate calculations, which they are. You can also consider x and y. So there are like 13, 14 calculations here. But, you know, combined all of this, it's like nine bullet points. And this is still going to take like 30 minutes for the untrained person, right? Going through all of this. So, yeah. Let's take a look at an example of this. Again, we're not learning any new calculus right now. We are just going to take a lot of algebra, pre-calculus, and calculus that we learned so far, and we're just going to put them all together and then combine them with that section, if you remember 3.2, where you learned how to sketch those graphs and so on. So all of that now is going to be very, 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 very relevant. Now, let's pick an example from the textbook, and you guys hopefully will be looking into the go over the examples that are done in the book as well. I'm going to pick whatever. Give me a number: 16, 18, 20.
19.
19 it is. F of x is equal to x to the 4th minus 6x squared. So there we go, right? And we have a couple of these things that we would like to solve about this so we can graph it without use of technology. We're going to start with the domain because that's usually the easiest. And in this case, negative infinity to positive infinity, because you can literally plug in any number you want into your function above. Then we have x-intercept. And when you're solving x-intercept, right, you learn in the algebra course that you set y equal to 0. So in this case, it will be x to the 4th minus 6x squared equal to 0. And to solve this, right, you will factor out x squared. Then you will get your x squared minus 6. And you will get x equals 0 and x equals plus minus root 6 as answers. So we already have three points that graph goes through. We have a 0, 0, we have root 6, 0, and negative root 6, 0. So we have 3 points, and I'm going to keep highlighting all of the information that we are using to graph. Now, these are x-intercepts, which means that eventually when I draw x-axis like this, I will just place these 3 points and the graph will go through those in some way. So that's the first thing. Now, this one is also a y-intercept because once the function crosses in some way through 0, 0, it crosses through x and the y-axis at the same time. So, and you can only have one y-intercept, obviously. right? So if you have a y-intercept there, you can't have another one there because then fails the vertical line test and it's not a function. Yet we are graphing functions. So once you get 0, 0, that means that's your x and y-intercept at the same time, plus the other two x-intercepts. So those are the points that we use. Now, asymptotes is none. Now, some of you might say, yay, but that's actually really bad. When the asymptotes provide you with extra guidance to, you know, snake these lines through, right? So functions have to follow asymptotes, and in case of the vertical asymptote, they can't cross it, right? So there is a lot of utility in having those asymptotes, and it's always a really sad situation when we don't have an asymptote of any kind. It tends to be harder to graph those problems. So let's have a moment of silence for 3 asymptotes that, you know, none of them being present with us now. All right, so now the next one is to find our derivatives. Now we have our f prime, which is 4x cubed minus 12x. And we have our f double prime, which would be 12x squared minus 12. So these are our derivatives. And yes, we are not graphing these derivatives, but I have to highlight them so I can find them quickly, because the next is what we learned last class, first and second derivative tests. So this is going to be a good review. FDT, first derivative test, is going to set the first derivative equal to 0 to find the critical points. Then we're going to do our partition, and there we go. So to solve this, we factor out 4x. What's left is x squared minus 3. And when we solve these, we get x equals 0 and x equals plus minus root 3. So these are our critical points. And now I also have no asymptote, no VAs, no vertical asymptotes. So when I do the partition, domain tells me that I have to partition everything from negative infinity to positive infinity. And then we put these partitions where we have the critical points. And then we pick the values as test points in each one of the regions. So a root 3 is smaller than root 4, right? And root 4 is, the square root of 4 is 2. So we can pick 2, 1, -1, -2. I mean, if you don't want to play, you know, close to the fire or something, you can just go and put 100, and there you go. But I'm going to put 2 because, again, square root of 3 is smaller than square root of 4, and 2 is square root of 4. So clearly 2 sits well in this region at the end. So now we have 4 regions, which means we have to test 4 values, right, in this. We have to test 4 values in this, what do you call it? In the first derivative test, right? So we start with first derivative equal, plug in. So first derivative of -2. So we plug in -2, and that's going to replace, right? So 4 -2 cubed minus 12 times -2, and that gives us 4 times -8 plus 24. 4 times -8 is -32 plus 24, and that gives me, I don't care, it's negative, I really don't care what the number is. I just know that 32 is bigger. The 32 is bigger than 24, and 32 is negative. So the number, whatever number it is, I know it's -8, but what I'm saying is I don't have to compute it because we don't care that it's -8. We just care that it's negative. So it's enough. If you know that the number is positive or negative, that's all you need for the first derivative test. Now we're going to also have the -1 calculated as the first derivative. That's going to be 4 times -1 cubed minus 12 times -1. And that's going to give us -4 plus 12. Now that's positive. Again, I don't care what the exact value is. I just know it's positive. Then we have the first derivative calculated at 1. There we go. Minus 12 times 1. That's going to be 4 minus 12. Well, that's going to be negative. So I'm going to put another decrease here. And finally, 2. That's 4 times 2 cubed minus 12 times 2 is equal to 832 minus 24. That's positive. 32 is bigger than 24. And in this problem, it turned out that it alternates. It alternates for polynomials. It doesn't alternate for others. So you have to be very careful. There are problems where this is not going to alternate. So you should always, just to be safe, you should always compute it. If you take a look at 1 over x, whose graph is the one you memorized and used so many times, you see this one is a decrease, and this one is a decrease as well. So it's a decrease followed by a decrease. So you can't just compute the first one and alternate all of the other ones. It depends on what kind of a function you have and whether that function is going to alternate or so. Polynomials always alternate, but then this additional piece of information that you're memorizing. So I'm not in favor of that, right? Just take a minute, compute these things, and there you have it. Now, can anyone remember what is the thing that I get for free when I do the first derivative test and we do this calculation and find intervals of increase and decrease? What do we get for free?
Max and min.
Beautiful. The max and the min. So when I observe this, I see that there is a minimum at -√3. I see that there is a maximum at 0, and I see that there is another minimum at +√3. Now we already know that this point is 0, 0, and I just need to compute -√3 and +√3 in the original problem to get the y values, right? So I can write these as x, y. So we go with the there we go. We go with the -√3 over here, and we raise that to the 4th power, -6, and then -√3, and we square that one. So this is 9 minus 6 times 3, and that turns out to be -9, right? Because you have 9 minus 18. So that turns out to be -9. And the other one, since it's symmetric, better be +9. Sorry, -9 as well. And we have 0, 0. So these are the points that we are actually graphing. So I'm going to highlight that. And also, this is information that we would need for graphing. I don't want to highlight it because it makes it ugly, but it's right there. second derivative test. So now you take your second derivative and set it equal to 0. It's 12x squared. All right, I'm going to give you 18 seconds to do this. No pressure. All right, so there was plenty of time for the second derivative test. So we set it equal to 0. We factor out 12. We have x squared minus 1. And that gives us plus minus 1 for inflection points. This is what we did last class. So now that I have inflection points, I do the partition. No vertical asymptotes, because we have to partition over inflection points and vertical asymptotes. No vertical asymptotes, so we're going to our negative infinity to positive infinity, and then we go with this. You put negative 1 and positive 1, no vertical asymptotes, so now we just pick the test points, and we can use again negative 2, now we can use 0 and positive 2. We do the second derivative test by plugging these values into the derivative. So we have 12 times negative 2 squared minus 12. That's positive, because when you square a negative, it becomes positive. So you have 4 12s minus 1 12s is 3 12s. That's positive. So that goes concave up. When the second derivative is larger than 0, we get concave up. Then we have the second derivative 0, which is 12 times 0 squared minus 12, and that's going to be negative. Concave down. And the last one is concave up, because, as I said, polynomials alternate. So, yeah. Polynomials alternate. The other functions, not so much. I mean, trig functions do and so on, but whole bunch of rational and do not. That's a 2 there, squared minus 12, and you are still getting larger than 0. Now again, if you don't like the analysis of these, that's fine. You don't have to do the analysis. You can go to the calculator, get your decimals, and say, okay, the number in the calculator is bigger or smaller than 0. That's all you need. So once you know that the test point gave the derivative, the test point allowed the derivative to be computed at positive value, then it's concave up, and if it's a negative value, it is concave down. So I technically have enough information to graph this, but I'm still going to push a little bit further and say, is this function even? And the answer is yes. Because you have x to the fourth, what do you have? Minus 6x squared. You can see that it only has even powers, right? And if it has even exponents, right, even powers, that means that it is symmetric on the y-axis because it's even function. Examples of even function would be, perfect example would be a cosine, right? Because cosine goes like that and then goes like this, and you can see it's symmetric on this middle line. Another perfect example is u squared, right? You see it's symmetric on the y-axis again because one part of the graph looks exactly the same as the other part of the graph. It's just in a mirror image. So we know the function is even, and because it's even, it has this symmetry through the y-axis. Now, you can also get the odd function, in which case it's symmetric to the origin. And we're going to see, hopefully, an example of that. I mean, we'll check every time, and then when we run into a problem with it, I'll point it out. All right, so I have all of the, I'm not going to compute the additional points. That's done only when you have to, because computing points in function is annoying and tedious, and and that's the reason why we have all of these things, to kind of just not compute numbers. Which I know it's a little bit controversial for a math class, but still. So let's see. I mean, the statement, right? It's controversial. Let's draw one of these XY coordinate planes and see what we can get here. I remember there was a 0, 0. Now, what I'm going to do in this problem, because I can, is I'm going to use 2 squares for my x values. Now, obviously, it's crucial to have the graph paper. It's crucial to be very picky about all of these things if you want to get it right. So what are my value? Oh, we have a -9. Sheesh. We have to have a different scale on the y-axis. That's okay, we'll live. That's -9. And we also need the +9. I'm going to move all of this stuff. Is the function even? Yes, because all exponents are even. There we go. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where the 9 is. All right, so all I need to do now is to go and collect all of the information that I highlighted earlier, not the derivatives, obviously, and place all of that stuff here. Again, unfortunately, we do not have asymptotes. So yeah, we can all have a crying session about it later. Now, let's focus on the things we do have. And that is our intercepts or at root 6 and negative root 6. Now, how much is root 6? It's about 2.5. I don't care exactly, right? It's somewhere in there. Because again, how do I approximate root 6? This is why you shouldn't be immediately jumping for a calculator, because every time you do that, right, one of your brain cells dies. Root 6 is in between root 4 and a root 9, which are the closest ones that you know how to compute. Now, root 4 is 2 and root 9 is 3. So call it, I don't care, it's not 2.5, but it's good enough, okay? It's good enough. I did not have to go and look for a calculator. Now, I will show you next week, definitely, how to compute this root 6 by hand without a calculator, because that's going to be a section here in calculus. But for now, this is good enough. You know, 6 is almost halfway between 4 and 9. Good to go. If you want to be more picky, put 2.4. There you go. Whatever. I don't care. I'm just going to put the dot right there. Say root 6. Put a dot right here. And call it negative root 6. Now, I also found out that 0, 0 was a maximum. And when something is a maximum, we get to put a little frown, right? A little frown on the maximum. And we found two minimum values at negative root 3 minus 9. Oh, I didn't have to go all the way up to 9 on the y-axis. Whatever, that's the y-axis. So I need root 3. How much is root 3? Well, root 4 is 2, right? And then you have root 3, then you have root 2, then you have root 1, which is 1. So it's about, 1.7, 1.8. You can't precisely draw that, down to the micromillimeter or something, micron. So just put it somewhere and then go down to your minimum, and remember, minimum is a smiley face. So this point here is your root 3 negative 9. Now you have over here another root 3. That's going to translate right here on the negative 9, and that's going to be another minimum. That's a negative root 3 negative 9, and that gets its own smiley face because it is a minimum. So two minimums, two smiley faces, one maximum, one frown, right? And then those 3 points on the x-axis that the function goes through. All I need to do is to, play the game of connect the dots, which is what you know from, from your, whatever, when you were 5 years old, 4 years old, whatever. There you go. There you go. There you go. There you go. Now, there are these points here and here that cut through negative 1 and 1, which were inflection points. I did not label those, unfortunately. Oops. Come on, tablet. Don't do that. There we go. You find their y values as well. Those are where the concavity changes. So now I'm going to use this graph to check against increase, decrease, concavity, and make sure that everything, because I really didn't use those concepts, the concept of concavity or increase, decrease on this particular graph, because the graph is too easy. I really didn't have to use them. It was enough for me to just go ahead and It was just enough. Just watching what's happening on the stream, is something is blinking over there. It was enough for me to just connect the dots from what I had for the min and max and all that stuff. But now, what we should see is we should see the interval from negative infinity all the way up to negative root 3 to be decreasing, and then another decreasing, right, on 0 to root 3. There it is. You can see the decrease and you can see the decrease. All right, now let's change the color into whatever the hell this is. Rose. Okay, rose. And the rose has increase on these intervals, which actually matches perfectly, as you can see. So, because this is where, right, your root 3 is and your negative root 3. So those are the values. That's it. Those are the values. So now, concavity. Now concavity changes at these inflection points. So I should see concave ups and concave down and all of that stuff, and we do see it. Let's go with this green. From negative 1 on, so this interval here is concave up, and this interval here is concave up. And you can see that on the chart. Concave up, concave up. In between, marked in yellow, I guess, is going to be the concave down part, and that's that U shape, flipped U shape. So your intervals are 2x values. Your intervals are 2x values, and something happens, right, with the graph between those 2x values. So graph is increasing or decreasing, or concave up, concave down, right? It's the interval that we are looking for. So now the graph is, what it's supposed to be without these colors. I just wanted to connect these intervals up to those little graphs we did, right, with the partitions. And yeah, that's that. Now let's take a look at something more interesting and see what the graphs would look like. I have done 33 on stream for the other class, so if you go and watch that one, you can find number 33, and I did another one with trig, I believe. I want to work on let's do 32, but I want to modify 32. So this is not problem 32 because I want to modify. Oh, but if I modify, then probably those calculations with derivatives and critical points and all that stuff is not going to work out because I changed it. I don't want to do the same problem, but then I guess I will have to. So problem 33 is one of those problems where you have to deal with the asymptotes, in particularly slant asymptote. So we start with the domain. Knowing that the numerator doesn't factor at all means that our domain is just negative infinity to negative 1/2 union negative 1/2 to positive infinity. The only interruption in the entire domain is at negative 1/2, which creates 0 in denominator, so that's a vertical asymptote. There are no other interruptions, so we just go there. And then we have our x and y intercepts. So x squared plus 12 divided by 2x plus 1 equals 0. And when you cross multiply, you get x squared plus 12 equals 0, and that has no real solution, which means no x-intercept. And that's a big deal. This means that the function never crosses x-axis. So everything is happening below x-axis or above x-axis or in both regions, but the line never goes through x-axis. That's a big statement. Now again, we don't like that because we have less information to graph. That's, such is life. Y-intercept is when we set x equal to 0. And in our case, 0 squared plus 12 divided by 2 times 0 plus 1. The whole thing is 12. So we have a 0, 12 y-intercept. So 0, 12 is something that we will be graphing. Asymptotes. Well, we already discovered the vertical asymptote at x equals -1/2. Again, in this case, you do not have to, reach for the sledgehammer called limit, because again, there was nothing special going on with this problem. You definitely can set the denominator equal to 0 and see that it doesn't work, right? So you can claim your vertical asymptote there. Now, if you still go and use your limit procedure from chapter 2, that's great. So we know the vertical asymptote. Horizontal asymptote is none, because the degree in the numerator is larger than the degree in the denominator, and if you are to take the limit of that as x goes to infinity, you are not able to bound that at the end. So no horizontal asymptote. But the slant asymptote is yes. And the slant asymptote is that y equal mx plus b line, which is an asymptote. I mean, x and y intercepts, x and y axis, when they are the barriers, right, is just a function x equals 0 and y equals 0. So in this case, we have to divide. We have to do the long division to find the equation. So yes, because x squared is, no, because the degree of x squared is by 1 larger than 2x. So your term with the highest exponent in the numerator is x squared, and then the highest degree in the denominator is 1. So now we do the long division to find this, and that's what we have to go 2x plus 1 divided into x squared plus 0x plus 12. I place this, what we call a placeholder there, so that we can easily do the division. So how many times 2x goes into x squared? If you don't know the answer, just do it on the side. X squared divided by 2x. When one of the x's cancel, the form of your answer is 1/2 x. That's what's left. So 1/2 x. You already know the slope, right? By the way, why they have to be 1 apart? They have to be 1 apart because when you are dividing, you have to get a single x, linear x. the formula is y equal mx plus b. So you can't have this one as a square or a cube or whatever, right? It has to stay x to the first power. And there it is. So now you have your slope in this. So now you multiply everything back, you get your x squared plus 1/2 x, and then you subtract these things. So what you get is negative 1/2 x, and you can drop down plus 12. Now you're asking yourselves how many times 2x goes into negative 1/2 x. So negative 1/2 x divided by 2x, and when x's are cancelled, what you get is, anyone? What's a half of a half?
Quarter.
Thank you. I was getting concerned, right? So minus a quarter. And then we actually don't care to multiply it back and all of that stuff because we already have y equal mx plus b. So all I need to do is to now claim that the slant asymptote is y equals 1/2 x minus 1/4. Now that's information we want to graph. This is information we want to graph. So those are our asymptotes, and they will guide this problem, the graph for this problem. Time for calculus. The first derivative, and then the second derivative after that. So now, what is the first derivative of our problem? You know what? Let's write f first, because I don't want to scroll up and down. X squared plus 12, 2x plus 1. So f prime of x is 2x plus 1 squared, then put 2x plus 1 over here, and then take the derivative, then minus, then x squared plus 12, and then times 2. Could you have done this in one shot with using the logarithmic? Yeah, of course. Again, do you really carry your sledgehammer everywhere? This was very, very small calculation. What do I have? I have 4x squared plus 2x minus 2x squared minus 24 divided by 2x plus 1 everything squared. And when I combine like terms, I get 2x squared plus 2x minus 24 divided by 2x plus 1 everything squared. So one more time, that's a 4x squared, that's a 2x, that is a negative 2x squared, and that it's a negative 24. So now we need a second derivative. So we're going to get this, there we go, blue, and then we're going to move to the second derivative, and the second derivative is, again, we have this 2x plus 1 now to the fourth power. We have 2x plus 1 over here squared, then derivative of the top, which is 4x plus 2, and then minus, copy the top, which is 2x squared plus 2x minus 24, times the derivative of the bottom, which is 2x plus 1 to the negative 3, no, that's it. I have 2 jump down, then I do these calculations, that one, and then times 2. There we go. So,
are you multiplying by 2 twice for that second half right there?
Yes.
All right.
Because this 2 is the one that dropped from here for the derivative. The other 2 is the chain rule from the inside. Right? You are taking the derivative of 2x plus 1 squared. So this 2 is going to jump in front. So we're going to have 2 times 2x plus 1. And then this 2 jumps out as a chain rule. So it's actually 4 altogether. All right, so now we have, we can cancel one of these. And let's see what the second derivative tells us. We have to FOIL this and then minus whatever is left over there. So 2x plus 1 cubed, always nice to have that done quickly. So now multiply, it's going to be 8x squared. That's 4x and 4x plus 8x. And then plus 2. Minus, and now this one gets multiplied by 4, 8x squared minus multiplied by 4, 4 times 2 is 8, 8x, and then plus, and now you have a 24 times 2 is 48, 48 times 2 is 96. And we simplify. Now, it's beautiful the way this simplifies. That's gone. That's gone. So all you have is a 94 up there.
Wouldn't that be 98?
That's what I said. Please pay attention. Yes, thank you. That is 98. And we have our second derivative. Look how it nicely collapsed into this one simple calculation later on for our second derivative test. But now, before we hit the second derivative test, we have to do the first derivative test. Oh, I forgot to do this. There we go. First derivative test, we take our first derivative, 2x squared plus 2x minus 24 divided by 2x plus 1 squared. Oh, thank you, YouTube. So I missed a cube over here. Please make sure it's cubed. So first derivative test equal to 0. When you cross multiply, denominator dies. So you have your 2x squared plus 2x minus 24 equals to 0. Now you divide it by 2 because all the coefficients are even. And you get your x squared plus x minus 12 equal to 0. And this is a good one because we have x plus 4, x minus 3. Right, that's the basic algebra factoring. And you get your x equals negative 4, the x equals 3. Now, those are your critical points. And we do the partition. Now, remember, your partition has to involve vertical asymptote as well. Right? It's not there for decoration. So we'll have to be careful about that. When I partition, I need to partition at the -4. I need to partition at -1/2. That's the vertical asymptote. I need to partition at 3. And that's it. Now we are going to use the test to compute, first test points. So -5, -1, 0, obviously, and 4. So you always try to pick a 0 because that kills a lot of calculations, which is good. So now we do the test. F prime, -5. Now f prime is 2x squared, so 2 -5 squared. What else was there? Plus 2x minus 24. Plus 2 -5. I think it's a plus 4. No, 2x minus 24. There we go. This is going to be 25, 50. Yeah, it's going to be larger than 0. Plug in -1. Again, this one does not have to alternate, guys. So, be careful about that. Plug in -1, that's 2 -1 squared plus 2 minus 5. This is plus 2. But the value I'm plugging in is -1. So this should be first derivative. Oh my God, I didn't do any. Guys, hold on. I did not divide this one. I wrote it up. You can see how 2 is not in line with the equal sign. I wrote it up so I can put the denominator. I was looking for what is missing. Why do I feel weird? I don't know though. When someone sometimes say that you subconsciously feel weird when even when your conscience did not recognize it or seen it or something. Well, that was the feeling that I had right now. Like something is wrong. And I did not compute the denominator. I mean, it's not going to change anything because it's squared, but still 2 times -5 plus 1 squared needs to be there because that's the entire thing for first derivative. So now, first derivative test. So now we already determined that the number on top is positive because -5 squared is positive 25. And then you go with the multiplication by 2 and so on. So when you get all of these together, they're still positive. They're still positive. So you have a positive divided by a positive, and that's just going to give you a number that is larger than 9, larger than 0. And now you just need to repeat this couple of times. So f prime at -1, that's going to be 2 times -1 squared plus 2 times -1. Well, parentheses missing over here. I erased something and then they were gone. Plus 24 divided by 2 times -1 plus 1, everything squared. So what we have is a positive plus a negative. So these guys actually cancel because they're both, one is -2, the other one is 2. So I have 24. So again, I have a positive divided by a positive. So it looks like this is increasing as well. Now, when you plug in 0, there's nothing easier than plugging 0. That's -24 over the positive number. So that one is going to be a negative. And now, do you see how it's increase, increase, and then decrease? So this is why you can't just memorize and alternate. You have to compute. So now f prime, oh, come on. F prime at 0 is 24 over some positive number. We know that that's 1, but whatever. So positive divided by positive is positive larger than 0. And the last one, the last example here is at 4. There we go. So that's 2 times 4 squared plus 2 times 4 plus 24 divided by some positive value. I don't care. So that's going to be 32. This is all addition, so it's positive over positive larger than 0. And that's exactly what we were expecting. Maybe, maybe not. Now I don't like how I have, no, I have to recheck. So that's positive 25, that's 50, that one definitely goes up. Then this one, negative, no, that's a positive 2, minus 2. So positive 2, minus 2, and then you just get 24. Okay. Now, that is a positive.
Is 0 greater than, or is f prime 0 greater than 0 or less than 0? Because you said that it's greater than 0, but then in the chart it's pointing down.
No, it's pointing up.
No, for 0.
Oh, for 0. Well, let's. Ooh. Positive divided by positive. And did we have? Oh, we haven't done it yet. Yes.
This might just be me, but shouldn't it be minus 24 for the f primes?
Yeah, that's what I thought.
Well,
That
is just going to change everything. Just. That's negative divided by a positive gives you a negative value. So f of 0 is negative. So going this way. The top, we have 50 minus 24. That's still good, right? -5. -5 squared is 25. That's a 50. And then 50 minus 30 something. Yeah, that's positive. That's good. Now, -1 is negative divided by a positive. That's a negative. So this one goes down. And then f4, yeah, it goes up because you have 32 plus 8 and then minus 24. So yeah, that's good. That's all good. All right, so look at the pattern. It's not increase, decrease, increase, decrease. It's decrease, increase, no, decrease, increase, decrease, decrease, increase, right? So they do not alternate. And I think this is a good exercise to see that. All right, cool. Second derivative test. Come on. Second derivative test. We take the second derivative, which is very, 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 very easy, which is 98 divided by 2x plus 3 cubed. Set equal to 0 and no solution, which gives us no inflection points. Now, as I said before, you should not be celebrating, right? Because you have less things to guide you. Now, we still get to partition, obviously, because even if you have no inflection points or critical points or all of this, right? If you don't have it, you still might have an asymptote. And if you don't have literally anything given, then through computation, then the entire domain is one partition. But we do have -1/2 to partition here. So that's it, from negative infinity to positive infinity. So no solution means no IP. IP stands for inflection point or internet protocol, whatever, depends which class you're in. So pick two values, clearly -1 and 0, right? That should not be hard to pick. And then we do the second derivative test. So f double prime of x is equal to 98, not of x, sorry, of -1, is 98 2 times -1 plus 3, 2x plus 3? It's 2x plus 1. So I have -1 cubed, so this is negative. So less than 0, so that's a concave down. And double prime at 0 is just going to be 98 divided by 1 cubed, which is positive. Concave up. There we go. So that's the derivatives. Symmetry, well, we don't have to bother with symmetry here. Where is the problem? You can see it's not symmetric. Well, I don't know if you can see it or not. I can. It's not symmetric, so I just leave it at that. No symmetry. Oops. Okay, time to graph. Now I recall one of these points had a very high, was that 9 or something? 12. 12. That's far up. So we are going to now draw the XY coordinate system, go all the way up to 12. So let's call this one 13 and this one called 12. And this is where the bottom is. Now, the first derivative, you told me this earlier, the first derivative gives you for free minimum and maximum. Now, being that I already did this problem before, I know that this is -4 minus 4, and I know that this one is 3, 3, and those are your, as you can see, this one over here is a max, and this one over here is a min. Now, before some of you freak out and say, ah, minimum is lower than a maximum, how's that? Well, it can be, right? Remember that minimum can be lower, maximum can be lower than the minimum, right? And we will see this now on the graph. Now, for this graph, I'm going to use two squares for 1 unit, because I have to graph that vertical asymptotes at -½ right here. So here's my vertical asymptote at half. -½ sorry, -½ Now we do know that we need -4, 4. So this is our maximum. So it gets a frown. And then 1, 2, 3, 1, 2, 3. That one is a 3, 3. And that's going to be a minimum. So we're going to give it a smiley face. We have one more asymptote. And that's the slant asymptote of 1/2. So I'll put this in blue. Y equals 1/2 x. Was that minus or plus 1/4?
Minus.
Minus, thank you. Minus 1/4. Now that is extremely difficult to graph because my divisions, right, on the y-axis are this 1 square each, right? So we can, I mean, what I can definitely do, because I'm on a tablet, is, right, to go in and find my -1/4. So if this is the half, then 1/4 is right there. Now my slope is 1/2, meaning 1 unit up, 2 units to the side. So now I'm in this zoomed in state. We see that my 1 unit up would be 1/4 before number 1. That's a 1 unit for y-axis, because 1 unit is 1 square. But to go over 2 has to go all the way to number 2. And now we connect these two. Now the x-axis is terrible. It should be, you know, a little bit up, but it's, yeah, I don't have. I am banished to the basement to teach. Obviously, right? Our government, local government here, closed the schools, so we can't go to school, and I can't teach from the upstairs because the kids roam free. So I'm trying to teach over here from the basement, and I don't have enough room to put all of the stuff that I need. Anyway, so I can't draw these lines very well. So we have the something like that, and then we just need to follow this out forever on both sides to the best we can, right? And we do have the intercept here at 12 on the y. There we go. And now we just need to connect the dots. So I know that 3, 3 is my minimum. So I'm going to go out of it into this intercept and then follow my vertical asymptote forever up. So like this, and go follow it up. That was a bad curve. No, please don't do that. Trying to erase it. There we go. On this side, it will follow this asymptote. Same thing happens here, except on this side, it will not cross anywhere. And it will go to the, oops, it will go to the left to meet with this asymptote. I mean, it will not touch it, it will follow it. And now if I need to zoom out so you can see what the graph looks like. Now obviously what you should do, the first thing what you should do is you should go onto the software, right, and graph this and make sure that it matches the graph you drew by hand, just to make sure that they work together. All right, so that's it for the graphing for today. I am going to work over one more problem next class, maybe two, and then we'll go with the next section next class, because we have to switch to do our review. So let's take about 5-minute break, and then when we come back, because we've already been here an hour and a half, when we come back, we'll do the review.